All right, everyone. So we're going to get started now. Christine is going to sort of guide us through this exercise, and others will sort of have a bigger conversation and pop in and pop out. So always, if you have any questions, feel free to interrupt, and we'll post this recording afterward as well. So with that, I will hand it over to Christine.
All right, thanks, Charity, and good morning, everyone. Thanks for joining us. Before I sort of dive into the notebook here today, I want to just make a couple plugs for how you can interact with us. So we've got a hashtag you can use on Twitter to share our session once we post a recording or ask us questions about the stuff we talked about. I've got a link to that in the Jupyter Notebook, hashtag Cooking with ClarityNLP. We also recently made a public Slack, so anyone can join that. You don't need a .edu domain or any other restricted domain. There's a link to that as well. And we strongly encourage you guys to interact with us and share Clarity with your coworkers, your friends, other people that are working in the same space. The cooking sessions in particular would benefit from user input and from direction, basically, from the people that want to use this stuff on terms of what you would like us to cover. So we are very receptive to that kind of feedback, and like I said, there's several channels for you to give it to us. If for any reason you want the feedback to be anonymous, you can just make a throwaway Slack, and that's fine too. We won't be offended. We're just mostly interested in getting your suggestions so that we can make sure that these sessions are as relevant as possible. There are also links in the header of the notebook for Clarity installation if you're just getting set up with Clarity for the first time. We have previous cooking sessions that are specifically dedicated to that type of content, so that can be helpful for troubleshooting and for getting up and running. So I strongly encourage you to check those out as well if that's the use case that applies to you. So I'm going to begin today with just some high-level background on what we're trying to do and how we arrived at this drug label and adverse event extraction problem. So we are currently participating in a challenge, which is the FDA Adverse Drug Event Evaluation Challenge. There's a hyperlink. This challenge has been in progress now for about 2 weeks, and you do have to request access to the data. So I'm not really able to share it with you in its raw form, but I think some of the insights we can talk about would certainly be helpful if you're interested in participating in that challenge, or just learning more about the data and the types of data extraction problems that we have in the space. So the FDA challenge basically asks you to ingest a set of drug labels, which are provided in XML format, and they provide a set of ground truth labels. So an important distinction there between drug label and ground truth label, where of course ground truth label we were using in the machine learning context as a Boolean classification label. The labels basically, if you look in section 1.2, they appear in this format. Each label, ground truth label, has an ID, the length, which is the length of the phrase that is sort of being tagged as an adverse event, a reason, which is an FDA-provided category, a section, which is a section within the XML document in which it appears, a start, which is just a character offset, and then a type. And these sort of the types are indications about how the FDA and the Office of Surveillance cares or does not care for specific adverse events. In our opinion, all adverse events are worthy of analysis, so we have not paid too much attention to these types, but they are important for sort of bucketing the labels that we have. So I've sort of included some information about them in the notebook. And then there's also MEDRA information. So MEDRA is just sort of a medical or I should say clinical ontology, which is helpful for classification and hierarchical grouping of terms, and also normalization from a relatively specific term that a clinician might use to something that might be a bit broader, so that you can sort of group things that are often, permuted into a common term. So that's sort of the organization of the ground truth labels that we receive from the FDA. Now, there's a couple of problems, and they're probably readily apparent if you're working in space. One is that we only have ground truth labels for matches. So we only know sentences, or actually substrings within sentences, where an adverse event occurs. We don't have any zeros. And typically we prefer to work with this kind of data in a matrix form. So a lot of the engineering work of this task is sort of getting the data from XML to a feature matrix, where we are able to generate sentence-level classifications for each of the ground truth labels that the FDA has provided us. So I have a function here that just does some XML parsing. I'm not going to go through that. It produces a labels with information data frame, which appears here below. I'm sort of highlighting it right now. As you can see, each file is associated with a particular drug, and then there's the information, and then the description of the FDA reason, which is informative. You can take a look at that. We also go on to generate counts by reason. So as you can see, it's a relatively skewed distribution. Several type reason categories constitute the bulk of the data set, and then it trails off from there. So for example, adverse event only as instruction and general term are very commonly appearing in this data set. Pre-existing condition or risk factor, also relatively common.
Zoom a little bit.
Oh yeah, of course, sorry. Other categories, for example, overdose or withdrawal, AE from off-label, contraindication, occur with much less relative frequency. So that's interesting and obviously also potentially problematic. From a machine learning and classification perspective, there's definitely some class imbalance here. And certain things that we might be interested in extracting occur with relative sparsity within the broader data set. So mostly to sort of tie our work in this area to something that might be interesting and useful to you all on the phone and to others that may listen to the recording down the road, we've decided to focus on a subset of the labels that the FDA provides us. And this subset rather appears here below, so I'm highlighting it right now. We've grouped them into buckets. So bucket 1 refers to adverse events that are labeled indication, contraindication, or risk factor. Bucket 2 refers to adverse events that are grouped within the category of withdrawal and pregnancy, because these are relatively high-risk labels and just generally interesting, useful to be able to extract successfully. And then the last bucket is negation. And as you'll see when Richard talks us through the negation section, this one is particularly interesting because unlike some of the other buckets we reviewed where you can get a lot of value from seeing terms that are, both linguistically and clinically associated with the buckets in question, negation is more of a grammatical task. And the reason for that is just the way that negation sentences are constructed. Oftentimes the negation clause appears at the beginning of the sentence. Sometimes the thing that's actually being negated is in a subordinate clause, and you have to sort of look at the dependency tree to understand that grammatical relationship and carry forward the negation to all the terms to which it might be applied. So that's why we selected these terms, and just to give you some information in case anyone's interested or digs into the data, you'll notice quickly that pregnancy is not actually an adverse event reason. It is instead, it can occur with several different reason categories, the most common of which is contraindication, and then pregnancy will appear under the MEDRA information. So basically the interpretation there is that this might be a drug which is contraindicated for pregnant women. So that's relatively intuitive, but I thought it's worth mentioning. So as I mentioned earlier, one of the key tasks of this process was to generate sentence level labels, including not only, of course, the matches, but the non-matches. So I have some functions here which take us from the data as we received it to a feature matrix where we get information that is useful and in Boolean format. And I'm not going to go through those, but I would, of course, if anyone has questions, would be happy to answer those offline or in one of the channels that I mentioned earlier. And that matrix gets generated, and from here we're in a good position to start talking about what we refer to as sort of a human-in-the-loop review of the feature matrix and the sentences, and then rule generation. So the idea here is that you could potentially combine several different NLP methods to go from raw sentences with labels to, I'll call it a rule-based engine, but I would caveat here that the rules don't necessarily have to be as naive as some of the ones we'll present here. I think there's room for improvement and for building on this foundation and integrating more sophisticated techniques so that rules might be more properly understood as feature engineering, where the feature engineering algorithm can be as complex or as robust as you might want. And it's more about organizing the rules in such a way that you optimize down selection potential and improve efficiency, and of course, maintaining accuracy. So these are mostly just helper functions. I won't review them. The first bucket, like I said, that we took a look at was indication, contraindication, and risk factor. So the first thing that we decided to do was look at n-grams. So can we generate n-grams over each of the sentences? And in this case, we actually filtered the data frame to include only the positive instances so that we could begin the manual review with sort of a bias toward matches, right, where these things do occur. And what we notice in looking at these and when we group by each of the tokens and sort of count, right, the occurrences of unique n-grams, that it's a skew distribution. Few n-grams occur with high relative frequency, and then it's sort of a tail from there.
So in this case, Christine, so just we focus at the end of this. So these are indications. It's not a candidate indication, but these are the ones when it's indication, contraindication, risk factor. This example here of
this is just subset to indication.
One.
Yeah, that's right.
So these ones, not surprisingly, very commonly you're saying in patients with in patients with indication. Blah blah blah. That's a pretty dominant.
And that's in my sort of again. I didn't get a chance to fully develop the classifier functions here, so I just have like skeletons that I think we'll continue to build on this notebook. So if anyone's interested on the line, look forward to updates on this hopefully in the next couple of days.
Yeah, I think it kind of introduced like throughout this whole work and through this because you have such a small data set. I think one of the things you see, you certainly see the importance of like knowing the domain because these certainly have these FDA labels certainly have their own expressive way of how they express these kind of indications in this case or related to overdose or whatever. So I think it's important to keep in mind the domain. So that's true with like a lot of problems that you have and sort of NLP and machine learning and whatever. So I think being able to sort of explore and iteratively look at the examples you have, I think that's important. And I think that's sort of an example of, yes, you can plug and play, but you really need to have some domain knowledge, and this sort of exposes those common patterns and helps us gain some of that knowledge that we maybe don't have intuitively if we're not familiar with this data.
Yeah, that's amazing how many you can sweep up with things that are sort of like indication patients or patients with, or anybody with,
So
quite a few of them.
The skeleton that I'm highlighting here is sort of just like you're saying, Don, some of the initial patterns I observed, which are very predictably, right? Patients with, patients treated, patients who, et cetera, sometimes modifying patients, so like adult patients as contrasted with children, I suppose. Another interesting sort of grammatical observation is that you do see you see a chaining of indication references. So the actual sentence might say something like, for patients with blank and blank and blank, where each of those blanks are actually things that the drug is intended to treat. So that type of information, again, is also predictable. It's something we would expect. That type of information is easy to enumerate, and it makes sense to put it in a single sentence, right? So if you see one, the things next to it in a sentence may also be indications. It's unlikely that you would split that type of a sentence construct with something, for example, that would be contraindicated without grammatical information.
So you would mix the two. So that string probably did start with patients with such and such, and so
correct.
You would have a larger string of it. But you're saying you wouldn't have like an indication, a contraindication, and an adverse effect all in a string.
Well, you might in a sentence, right? But you would probably have like a prepositional phrase or a conditional, disjunction separating the two things. Would be my expectation. So that's interesting to consider. And to Charity's point, some of the indication information is recoverable from other sources, right? So, for example, we can get from other portions of the drug label that are not actually in this data set what the drug is intended to treat. So that would be a relatively naive matching. Do we see like drug A is intended to treat condition B? Is condition B in the sentence? Well, okay, then we know that it's drug A. We can leverage that type of information. And I think the same logic sort of extends to contraindication in the sense that we know that certain drugs are contraindicated for certain populations. So if we see a reference to one of those populations, we should probably flag it as contraindication. And on that note, the next data frame I have here is the filter for adverse events whose reason label was contraindication. So perhaps not unsurprising, you see several references to patients with severe blank, females who are, so generally being a woman is going to be a strike against you for a lot of drugs. Family history of blank, history of blank. So interestingly, also though, we can observe a similar pattern to indication. So for example, line 71, falsely numbered here, patients with N blank, we saw the same pattern above, but it was indication. So in some sense, the grammatical pattern is very similar. You need external information to be able to distinguish between these two classes.
But if you took the larger sentence, presumably it's all there. In other words, if it wasn't a 4-gram or 5-gram,
Essentially,
whatever it is,
yeah.
Somewhere along there.
Yeah, but I think it's worth noting that like grammatically they're very similar.
Yeah.
So it would be beneficial, I think, for this type of task to incorporate exogenous information to the extent possible. And then finally, we take a look at pre-existing condition or risk factor. So this, in my opinion, and John, feel free to like weigh in here if you disagree, but it seems to me as if it's possible that that's like a nested form of contraindication. For example, like having a pre-existing condition might make a certain drug contraindicated for you, and you do see similar patterns. Patients with a history of, patients with severe, family history, risk factors, women with, women during, elderly patients. Like there are certain classes of patients
it's
that we know.
softer version of a contraindication, like in a sense, like you may be predisposed.
Right. Yeah, so that's interesting to observe, right? It's a little bit more caveated, it's a little bit more probabilistic perhaps, because some of these things you might not know, like family history might go back further than you have access to. But some of the grammatical patterns and even terms themselves are similar to other categories. So in general, distinguishing between classes is probably more difficult than correctly labeling a single instance.
In some ways, though, one of our goals of lumping this group 1, 2, and 3 was that all of these would be caught together.
Well, they might be caught together if you made the Boolean label, is it in this group of 3?
That's what
Like,
is it in this group of 3?
Yeah.
As opposed to
Yes.
what we're not talking about today, which is the adverse effect.
Correct.
That's the big toggle, no toggle
right
thing. So it actually works out. You can say these are in bucket 1.
Yeah.
That's very
yeah. And if that's acceptable, I agree. That would actually be easy. It would certainly be easier than correctly distinguishing between labels in bucket 1. And that's an observation that I think you'll see like when Charity talks is also true in other types of NLP tasks in this space. Distinguishing between things where there's a potentially fuzzy line is going to require additional information. It's going to require you to leverage not just the semantic information, but also things you might know about the patient or the drug itself. And that information, to some extent, does exist in the world. So one, I think, potential next step for us is to consider ways that we might integrate it. Another, I think some potential next steps for actually developing these term identification and term sets with algorithms is that we might consider other representations of the sentences, so bag of words, TF-IDF, bag of words. We also might consider sentence level embeddings, and those could potentially be used for clustering, which allows you to assess cosine similarity, ingest new terms or new sentences, and classify them based on their proximity to previously ingested terms. And that could potentially be useful for understanding some of the nonlinear relationships that might exist here. So I'm going to turn it over to Charity to talk about bucket B.
Sure. So bucket B, what I wanted to do was sort of take some of the work that Christine had done and sort of convert it, think about it, how we might do it in Clarity, sort of expand upon that. We'll first talk about, we can look at the patterns, and I think that has some the same kind of things we see with indication and contraindication. So you see lots of series of lists. You see risk of, you see includes, you say while this is taken, you see warnings. So you see a lot of the same kind of things. Now, granted, that requires you knowing some of these keywords that we found in Medra, but as you can see, there are some very common patterns that can be identified within this data. So to take it back and sort of how we would maybe approach this another way, how we might explore this data, specifically with pregnancy, because this data set didn't separate those out. So I started with sort of what I thought were good terms, and then through iterative exploration, I built upon that term list. Do you want to hand over to me? I guess I can take over. Let's see. Great. All right, so now I am sharing my screen. So let's go now to ClarityNLP. So let's start with pregnancy-related terms. And if we look at this explore little window, sort of where I had these terms, I started out with pregnancy and pregnant and childbearing, pregnancies, fetal, fetus. But then as I started to review the data, I was able to find new things. So that's kind of what I wanted to show, sort of how we do this. A quick aside, a very, very quick aside. If you're curious to how to work with this type of data in Clarity, I can show that as well. So this type of data, it's pretty ugly. It's XML. It looks like this. So it's not the most easy and straightforward, as Christine mentioned with parsing. If you're curious about how you might parse that and load that into Clarity, I've checked in a really simple notebook here, which basically does that for you. So it sort of digs into that, if that's something like.
Is that XML specific or just?
It is XML specific, but it's specifically for this data, but it just gives an example of how.
The fields that are in that data.
Right. So mapping the fields that are in those files to Clarity. So just wanted to provide that as an example when you're working with these sort of ugly XML documents that is in there. So once I loaded all these drug labels into Clarity, I wanted to dig specifically into these pregnancy terms. So normally what we see is these are the most common drugs, and these are that mention pregnancy. And I think, I don't know, from a clinical aspect, John, did those sort of pop out to you? Like that?
Yeah, absolutely.
Yeah.
Thalidomide is number 2.
Thalidomide, yeah. So yeah, these are so these are things we see. So pregnancy, increased risks, paroxetine, first trimester pregnancy was associated with increased risk. So you can kind of see the same patterns, but this sort of gives you the fuller context if you wanted to explore it, and you can do some more things with this data. Obviously, this is the big one that we all know about, thalidomide. There's lots of risk and mentions of fetal toxicity, specifically things with birth defects. So this is useful. So we can see, okay, we're finding drugs that potentially mention, and we can sort of see a relationship. So the higher the frequency, generally, we can find, okay, that's probably likely to have, specifically in the case of drug labels, likely to have higher risk, specifically for pregnant women.
So you found those additional terms by just kind of as you were going through these results, you found some of those other like fertilized egg or things like that.
Yep. And then, so once I've done that, the next thing I did was I wanted to look at n-grams. So while we can take the same terms, we can do that with Texasy, you do it ourselves, but you can also, Clarity also has built-in functions to run n-grams. So I wanted to show if you had this data in Clarity, how you could do that. So the same kind of thing, I took the, oops, that's the wrong one. Sorry about that. Maybe I didn't run it. Well, here we go. So that's the one I was saving, yeah. So if we go to, let's copy this guy. Let me copy it. Specifically, we can run n-grams, and then we can see what results we get and see if it gives us information about the patterns that we see. So let's change this to pregnancy, and then let's go back and look at the terms we found. Hold on one second. So if we go back to our term list, then we can sort of tie it all together and see how we can do this completely with Clarity. So we got our pregnancy-related terms, and we'll copy those in. And then while this is running, I'll go on and talk about some other things. So here's that. So in this case, I did n equals 4. We can change the n here. You can filter out stop words, all this stuff I think we've talked about before. Minimum frequency might be important here. So we're trying to find patterns. So maybe I want to increase this to 2. So this sort of like lets Clarity do all that chunking, and basically I just have to tune these parameters. So if you want to look at how that runs, we'll see that in a minute. Going back to when I was thinking about pregnancy, I was also able to think about teratogenic effects. So these are sort of, you want to describe that, John?
Teratogenic effects are things that cause congenital abnormalities and.
Yeah, so that's a lot of what we see with drug labels. Specifically, so once I found all those pregnancy terms and I was able to do find the results around that, I was able to sort of dig into these terms, and I found additional information. So this was useful for like finding. So this is sort of what we expect. So in this case, specifically, drugs that have a high risk of causing birth defects, we see thalidomide at the top. A lot of things we see, fetal harm, fetal toxicity. So these are all sort of things I just found through exploration and sort of doing in grams of clarity. So just wanted to show those sort of patterns, and you can kind of see the same kind of thing running through ClarityNLP. So let's see if this is done. It shouldn't take too long. One second. Yep, so it is done. So not only can you look at them in this tool, if it's useful, so you can view them in Clarity. Another thing that's useful is to just download the results. So you can download, and then once you've done that, you can do sorting and things like that and sort of see via Excel. So Clarity gives you a count for each pattern, so we can sort of find maybe common patterns to help us find maybe risk associated with pregnancy in these drug labels. So let's sort by count, and we'll do largest, smallest. So these sort of like can cause fetal harm, which doesn't make a lot of sense.
Yeah, is this frequency based?
Yeah, it's frequency based.
That's unusual.
Yeah.
There's not that many, but it's still that's odd.
Yeah.
I think there's a lot of.
I mean,
There's
it could be
exactly
the
Like,
limit.
can
The,
cause would make sense, but can be cause.
yeah, it could be something with the limitization, but I don't know.
Yeah.
Oh yeah,
The pre-processing.
that's true. Yeah.
Yeah. So because I use limitization, that could be why. But because fetal harm.
I'm sure there's a cause. There must be.
Yeah. Fetal harm when administered, hazard to the fetus. Trimester have developed complications in the third trimester. So obviously, like looking at things in the third trimester, specifically looking at the fetus. This is sort of like another way to sort of, and let's hide some of these columns. Not that one. Sorry.
Assessment or patient risk prediction, you have to also consider people who are not pregnant but could become pregnant. So there's like a future progression that's possible as well to think about.
Yeah, so these are all highly related. So yeah, you can see like 30 weeks. You can see certain days and weeks and time periods within gestation, within lactation and breastfeeding. So these sort of time-based effects, time-based features are certainly important, especially related to pregnancy, obviously, because it's like there's a finite window there. So anyway, I wanted to, so that sort of gives you like, these are some examples how you might find this clarity. You can do the same sort of thing with overdose, because what we found with these particularly, like there weren't a lot of labels, and that's why sometimes it makes sense to manually review. So related to overdose and withdrawal terms, these are ones that specifically had a lot of mention, so we can look at the kind of things. So so discontinued, this is interesting. So when I was comparing my intuition with the labels provided by this FDA challenge, a lot of the mentions were related to discontinuation, where they had truth and I had a false, essentially. So it was related to when you discontinue a drug, you have a risk of developing complications. So I don't know that I would classify that the same way, but that's how they tend to be classified.
So they in their labeling classified, for example, gastrointestinal perforation here as a
Well,
withdrawal.
not specifically gastrointestinal perforation. I don't know if I can find the one that I use specifically. Specifically, let me go back here to. So this was particularly one drug. So discontinuing, particularly in the first few weeks after blah blah blah, increases the risk of subsequent this, and I believe in this case it was like myocardial infarction.
So discontinuing in the context.
So
Right, makes
discontinue.
sense, right? Like,
That
Right.
makes sense.
So this is where like I had to introduce, and this is certainly another area to explore. I didn't quite get this this algorithm and sort of like the right combination, sort of like rooted out just yet. But it's certainly some combination of things you would commonly think of overdose and withdrawal, but also sort of effects of discontinuation. Specifically, ones that were labeled were, I noticed, like related to cardiovascular effects, mostly, were the ones that I missed, which I thought was interesting. So I don't know, that may be just a particular of this data set, but it was things like myocardial infarction.
When you say you missed it, you mean
Well, so
using
I
search
missed it.
terms, or-
Yeah, using my search terms with ClarityNLP. So most of them I was able to just match up based on like overdose and withdrawal terms. But then I missed some, and these were these discontinuing might cause, a heart attack. Discontinuing might cause,
Okay.
which
yeah, and the engrams, like, I remember it also came up often, like, sudden, there were mentions of suddenness, which, again, tying back to temporal stuff, is like, stopping the drug is not necessarily problematic, but stopping it suddenly without, like, in cases where titration is required, for example, or where you have to sort of scale down over time, and you haven't done that, or you just abruptly are like, I don't
Yeah.
like these side effects, I'm not going to take this drug anymore.
So it looks like probably there were a lot of maybe false positives though in the search term, because a lot of
Yeah.
them were like discontinue the drug.
right. Well, yeah,
That
because
seems to be,
initially
like,
I
the
didn't.
dominant.
Initially I didn't do that, but then I wanted to add it to see if I could pick up those additional ones. But like I said, there's somewhere in the middle that's sort of being able to capture the discontinuing effect versus just discontinuation. So risks from discontinuation versus just discontinuation.
Yeah, like
So that's sort
the
of like
imperative
the
command to discontinue.
right, which doesn't really happen too much in as much in this data, but that's certainly like a thing to expand on and continue to build on if we wanted to find sort of risks
It's sort of like
of
where
overdose withdrawal.
incremental or marginal risk is increased. At least
Mm-hmm.
in these two examples here, but I think I observed that in engrams as well. So that sort of distinguishes it between the situation where they're just like discontinue if this thing happens to you that's
Mhm.
bad versus
Well,
if this and this and this and this, you're at increased risk for X.
yeah, I might say actually though in this case, not stemming. Like I think that discontinue is almost, there's going to be certain framings where it's like patients who discontinue blah 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 is going to be a withdrawal scenario, but other cases where they
Right.
discontinue,
As like
it is going to
right?
be like discontinue the drug, and that's probably more
Right.
common. Where something like discontinuation will almost always be a withdrawal
Mhm.
story. Something like discontinue will probably more commonly be a recommendation to discontinue unless it's framed right. So this is with the larger
Like part
Yeah.
of speech tagging.
the part of speech tag is going to be really
Yeah, expanding upon this is certainly like where it needs to. There's certainly more tuning and expanding that can be done upon this, but I found that to be pretty interesting with this data. So that's sort of things you find as sort of you go down the rabbit hole. So in this case, I was just comparing sort of the labels that we were given. Oh, here's another example. So stopping Brilinta increases risk of subsequent overdose or withdrawal. So these are all these same kind of
That
things.
second term is probably death. So the general term, death falls within that category because they don't consider it specific enough to be informative. So that's another observation from the engine for withdrawal is that much like the indication subset, we see chaining is pretty common. So
And
kind of inceptionist here for a second.
yeah, it's very inception-y.
All right. So now we're going to actually just pass it over to Richard, and I'll go through for Richard. So we're going to talk about negation next.
All right, I'd like to describe a different method of looking at this data. This is kind of labor-intensive method. It's really good for very clean data when you have nicely formed, well-structured grammatical sentences. Our data doesn't exactly fit into that, but we can look at phrases within the data and find some useful information. So what I want to cover is using a dependency parse to try to find terms of interest in a sentence. So a dependency parse is a way of encoding in tree form the syntactic relationships among the words in a sentence. And I have an example sentence here. The girl has a flower in her hair, and a visualization of the dependency parse tree using a tool called Displacy. We used the NLP library Spacey to generate this dependency parse, and they have an associated visualization tool called Displacy that generates these diagrams. So you may be wondering exactly where the tree is in all this. The root node of the tree is the verb has. You can see it's the third token over. And I know that's the root because I can start at the root and follow all the arrows and visit all the words in the sentence. Okay? So underneath each word of the sentence, you'll see the part of speech. Det means determiner. ADP is the symbol for preposition, if you're wondering what that is. And the arrows encode the relationships among the words. And the way that works is the term at the arrowhead end either modifies the term at the other end or is related to the term at the other end in a certain way as indicated by the label on the arrow. So if you look at the first arrow between the word the and girl, you see that the is at the arrow end. So that means the modifies the word girl at the other end in a certain way. And the relationship that it shows is the is a determiner for girl. Okay? If you look at the arrow between has and flower, flower is at the arrow end. So it's related to the verb has at the other end. The relationship is a direct object. That's generally how it works. It shows you as a tree the relationship between the terms in the sentence. So it's possible to use this dependency parse and come up with rules for traversing it that will let you find terms of interest. So we looked through our data set and we saw repeated occurrences of phrases that were relatively similar. For instance, I have a few listed here. We saw things such as no cases of X were reported, where X is some adverse event. No X occurred in any of the following whatever. No evidence of X, no evidence of serious X was detected, that sort of stuff. So we thought, all right, well, here's sort of a general pattern. We start with the word no. We have one or more X's, possibly connected by conjunctions or as part of prepositional phrases with additional modifiers, perhaps, then followed by verbs. So, all right, let's come up with rules for analyzing this phrase structure and see if we can use it to find the X in all of these phrases. Okay, so we thought about that a while and we came up with the following algorithm. What we came up with is you find the root token of the dependency parse tree. Okay, that's easy to do. Spacey gives you an object representing the dependency parse, and you can scan through it and find the one labeled root. And then you find the modifiers of the root token if it has any. And if it does have modifiers, find all the nouns in that list of modifiers. Then for each noun, get any prepositional phrases that modify it, or find any conjunctions and associated nouns that it is linked to. Remember, you can find all this by by traversing around in the dependency parse tree and using the link label to figure out what the relationships are. If you find any conjunction link nouns, you take all the nouns that are linked by conjunctions. If you find prepositional phrases, you keep the object of the preposition. Okay? So if we follow this relatively ad hoc but simple algorithm, we can use it to find the term X in these phrases that fit this pattern. So if we scroll down through the notebook here, we have code to do this. I'm not going to go through all this code in depth, but I'll just say that one key part of this is finding modifiers of a given token. The way you need to do that is a depth-first traversal of this parse tree, because you essentially want to visit all the leaf nodes of a given branch before you start exploring other branches. Because a given modifier word could have modifiers itself. You need to pick those up before you scan all the other modifiers. Okay? So this code keeps all that stuff sorted out. Just remember, you want to do a depth-first traversal of the tree. If you scroll down, we have other functions for finding modifiers, and then another function for getting either prepositional phrases or conjunctions.
How does a search tag differ from a starting token?
Search tag.
I thought I saw the word.
Which is a part of speech tag, right? The
Oh, it's a part of speech.
Yeah, like we're looking for preposition or conjunction. That's just a tag. That
Okay. I'm sorry. It's the tag that's assigned by this.
Yeah, there's a lot of data that's spatially appends to each term. That's just one tag there. Okay, so if we scroll down a bit, we can see our function analyze. That implements our algorithm. So this dot argument, that's the sort of spacey convention for the dependency parse. That's essentially a list of tokens, and each token has the term, and the tags, and various other information in it. So we scan through that token list and find the root. Then we get the modifiers of the root token, if any. Then we scan the list of modifiers and found any nouns that we can find. And then if we do find nouns, we get the modifiers of those nouns and then see if no is present, and if so, look for prepositional phrases or conjunctions. Or if no nouns are present, we then just get the targets for the node that we find. So pretty simple. Scrolling down is a driver program that does this. Essentially what this driver does is go through our data. Christine showed how she built this big matrix that has all the information for each, basically a row by row. You can find the sentences and the text associated with each term in there. We iterate through this matrix within a data frame. We extract the text, we tokenize it into sentences, perform some cleanup on it, and then run it through our algorithm. Okay, and we look for these X terms, and if we find any, we print out the token index and the label on it, which hopefully will be an X. So basically, if we find the X term, then our algorithm was successful. If we didn't find the X term, then either the sentence didn't fit the pattern that our rules apply to, or we just missed it. Okay. Again, we don't use any known labels or anything. This is purely built on the grammatical structure of the sentence. So if you run all this stuff,
and this is hitting the full sentence.
well, that's cleaned up by this other code.
The cleaned up sentence.
Yeah.
Okay, but yeah. Okay.
So we also though we did let the sentence link to 16 words. That's just arbitrary limit because
16.
Like some of these sentences go on for they actually have several sentences with hundreds of words in them.
And that's
just can't
sort
have
of an artifact of how the label extraction process happens.
Okay.
So
that's
because
optimal.
it's XML, because we're
Because XML is messy.
Yeah, it's very messy.
The real way to do this is to use the regular expression to find the pattern or general range where the pattern would be, and then
I gotcha.
analyze it with this dependency parse set of rules.
Fuck, go ahead.
All right. So if you run this, the results we get are here. Maybe Christine, you click on the left side of that and expand it a bit.
This one here.
Yeah, the output there. Just put that left. Okay, that's fine. Yeah, so here we see sentences listed, and then underneath it says targets, index 1, comma, text X. If you see a text X, that means it found the X token in the sentence. All right? So there are something like 50 or so sentences that satisfied our criteria, and I'd say it probably found the X in maybe 20 of them. We have a few errors in here, like text milligram text treatment. There's 3, 4, or 5, I think, that it got wrong. But for this, I mean, relatively limited scope of this pattern and relatively simple rules, you can see that you can use it to find.
So this is saying, when it says target, it means it found it.
Target is just its term for, here's the term I found.
But like, for example, sentence 14, it's saying, I'm not seeing.
Right, it didn't find anything for that.
I'm not seeing
target
it.
left there.
So that would be like a 0. If you
It's
go
a
back to
0.
the classification.
It's going back to classification.
Sentence 16, it found something, but it got it wrong because it found patients instead of the X label, okay, or the X token.
Well, if you did it say X or did it say text page? Can you go back to
It said text patient.
Okay.
Like 16 there.
Yes, it didn't get it wrong because it told you it found patients instead of X.
Yeah.
And
Well-
X is from Christine's replacement or something along those lines.
Right.
But that, yeah, so Richard's
Man, I just
grammatical
replaced
parsing doesn't find X because of the way the noun modification.
No, right. So you replace the X. But that's.
So bear in mind, just to note, maybe to clarify here, the data frame Richard is running this on, all of those are positive matches given the FDA label. There are some false positives because some of the sentences when I did the label extraction are actually multiple sentences.
I see.
So some of the error is that, and then some of the error, not error, but we don't expect all the sentences to match with one.
So all the X's are negated. No-nos are all this. No, whatever. They're the negation ones.
Yes.
So when it says
When it says
in
found
12,
X, it means
no patients had X, it's not linking. It's finding it, but it's not linking it to patients.
Right. It found the term patients instead of X. So the rules are too simple to disambiguate something like that.
Okay.
Now, we had lots of time. We've come up with more complicated rules to work all these out. But the point was just to show this is one method. It's
Can you slow it down? So it actually found X though, and like in a lot of these, it found X even though it was no cases of X or no whatever of X. There was no notable. So and then these ones that had no target were
those are
missed.
zeros, basically.
They either didn't fit the pattern or just couldn't find anything based on these rules.
Yeah.
And some of them, like I said, might be actual false positives. Some of them probably just grammatically are expressed differently, so the pattern fails.
And actually, if you look at the data set, some of the labels in there are erroneous.
Yeah.
So that might have something to do with it too.
But you could rerun this on any of the labels, right? You could do this on the contraindication one, and you could do this on the withdrawal one.
You could, yeah. The pattern may not be as relevant there.
Well, but I mean, you could
But
just
you could
run
try
it
it,
and see what happens.
And
Or the indication, for example.
Right.
Yeah.
And the reason we did this is so ClarityNLP actually uses something like this to figure out or to relate a measurement to what's being measured. Okay? In that case, we have it somewhat easier because we know where the measurement is in the sentence. And that's our anchor point. And we can devise rules for traversing the parse tree starting at that point. Here, we don't know where we're starting. So we start at the root. But ClarityNLP uses a technique similar to this to try to figure out the item being measured when you have a sentence of a measurement. Okay? So that's really the relevance
And
of this.
can you displace any of these where you can see the parts,
Yeah, you can
visualize the parts?
Yeah, you can go to Display C and just type the sentence in, and it'll do it for you.
No, that's
Link
good.
it.
That's good.
And just one other thing I would note here that's interesting, and like one of the benefits of this approach is that it moves us beyond regex, where you're relatively confined to patterns you can see based on the data you have, which of course limits your ability to generalize new data. Here we can think about patterns at the grammatical level, at the part of speech level, so it's much more flexible and potentially extensible. So that's something that's like a strong point in favor of this type of thing.
Right. But
Where we can expand.
what Christine just said is the key. It relies on part of speech and the ability of the NLP tool to accurately identify the part of speech.
Yeah, which
It
is a
tends to be a problem in medical text.
very, very good caveat to point out. Absolutely true.
So we have taken ways to counteract that, but anyway.
Yeah, the grammatical correctness is the strong point that that helps those kind of algorithms work well.
Well, it's not going to work as well for clinical notes compared to like a clinical trial write-up, where presumably there's some
Where they generally write
grammar somewhere or something like that. Right.
We spend the
Or even
last.
for medical paper.
Yeah. Okay.
Go ahead, sorry.
Oh, sorry. I was gonna spend the last 5 minutes just on our little demo.
Yep. Just take
So I'm gonna
Cool.
share my content. So thanks everyone. Just want to do one more quick thing that we've introduced into Clarity, and sort of ties back to all this that we're talking about. So the FDA, they give us some ground truth labels. Sort of one of the gaps we have had in Clarity is like, how do we know that the algorithms we're coming up with, the custom tasks, how do we know it's accurate? So the way we do that is sort of we can quickly and easily have user ground truth generated labels. So in this case, I can look at my overdose and withdrawal terms because that's where we saw some, problems. So in this case, I can just, this one looks right. Would you guys agree? Signs and systems of overdose. So we can click it. It gives us the feedback. So you can go through all these and you'd be like, yeah, this looks right. Maybe we can find some ones that, like false. Yeah, we definitely don't agree with that. Yeah, so these are wrong. So this is like, I can take this information and feed it back to my algorithm. So I sort of have all this, these quick buttons that you can have experts or if you're building algorithms, you can go through.
Chirag's polite, thank you.
Yeah, Chirag had very polite messages. I didn't change his UI. I had to rework some stuff on the back end, but I did not change his UI, but he was very polite. So if you go back and look at sort of how you can get these out, you can click this link called annotations. And basically what that does is you can download the truth labels that we just clicked. So this is handy because this is the feature that I ran in NLP. This is the report ID if I want to join it back. This is the result ID in Mongo. So for example, I can take this.
I guess we can ultimately add this to the feature.
You can, but I didn't want to assume that necessarily. So let's go back. So cohort. Essentially, you can via whatever, or we could do it for you. You can join these IDs, join with these result IDs, and then you can sort of create a matrix of your ground truth labels. So this is certainly something that we can use to feedback and improve our algorithms with ClarityNLP. So I just wanted to sort of show that capability off as we're talking about validating algorithms and labels and that sort of thing. That capability is now included in Clarity.
Cool. Wow. Awesome.
We talked about like down the road maybe we could get multiple annotators, right? To see like if they
Yep.
Well, that took us all the way through. Well, thank you so much, everybody, and thank you both for joining. And we look forward to type 2. We're going to go to, I think 2 weeks from now, we're going to do a FIRE and NLP integration as a possibility. But we actually more welcome, of course, suggestions for target topics that we can tackle. So thanks for that, Elena.
Thanks.